problem that we're interested in general is like if you would have some biosignal from the human, how can we create good, reliable machine learning systems, and how we should analyze the systems, how we should evaluate these machine learning systems to know whether they're doing well, etc. So in order for us to be able to accomplish our objectives and be able to test these different machine learning techniques, we needed to sort of have data that's already labeled and publicly available. So we have chosen Cogware dataset, which we will discuss about it. It's a dataset that's available in Physium. One paradigm is this conventional machine in which the feature selection, where you're actually sort of figuring out which feature contributing to the predictions, is being separated as a feature engineering step. And then we pass these things to machine learning models, more like data science type of models, XGBoost, logistic regression. And then toward the end of the presentation, we're going to sort of more modern approach of end-to-end deep learning, where we don't want humans to interfere with basically feature selection. So everything is going to be based on deep learning. And at the end, we're going to provide some summary of the result. The results are basically still preliminary based on Cogware dataset.
So what is Cogware? What does it look like? We have a database of these signals that are collected by smartwatches and an EEG headband. So we have access to different signals, the EEG, the BVP, similar. We picked one signal to start with here, which is the BVP data from the smartwatch. And the goal is developing tools for cognitive effort. So they take their test population, they hook them up, and they give them either a simple recall test, or they give them a Stroop test. The Stroop testing is where you have to name which color is written down in text, but the actual color is different. So it might read in text green, but the color's red, and you have to really think to tell the difference. So the baseline condition is the BVP signals that are collected during a simple recall, and the cognitive load condition is collected during the Stroop test. And these BVP windows, or these BVP samples, are separated for us into separate folders so that it's really easy for us to label them. I can say baseline, label 0, everything in this folder is 0. As how this directory is structured, everything in cognitive load, that's all label 1. And we can see the structure of the file. We have the actual BVP sample with the time that value was sampled. And we can reconstitute the signals and graph and do all of our processing and feature engineering out of data that's organized like this and is clearly labeled. So let's plot these and see what they look like, see if we have any basis for making a difference. In the blue, we have the rest condition, or the simple recall, and in the cognitive load condition, the Stroop test is in red. We can see our standard deviations higher, perhaps, in the cognitive load. We also notice that the pilots are fairly different from each other. So that's one of the difficulties. But one of the good things about this data set, there's 11 pilots, and we can look at all of them and visualize them all in 2 slides, which is kind of a gift. So we prepared our 3 pipelines. The first is to select features or process features out of those BVP signals, and then pass them through a logistic regression model in order to predict whether or not that sample comes from the rest or the Stroop test cognitive load condition. Our second pipeline is feeding in some of those same features that we've picked out with our logistic regression, but also feeding the raw signals into the deep neural network approach and seeing if we can get any increase in performance or stable result. And then the last approach is to actually do a Fourier transform, create a spectrogram, and see if we can pull out patterns using the transfer learning approach, where we take a model that's trained elsewhere and then we tweak it in the last step with our data. And I will say the primary challenge we're facing is that with 11 participants and each of their samples is less than 3 minutes long, we don't have a ton of data. So like I said, these are we're thinking also of ways to challenge the small data regime. And then we also have 2 different testing conditions. Again, facing down the small data regime, we have an individualized test. So in the individual case, we're picturing we have a different model for each participant because they are so different from each other. And then in the generalized case, we train on multiple participants and test on multiple participants that are different from each other. So let's get more specific. For the individualized test, we're taking 80% of that participant's data, and that's our train set. And then we have a 20% test set for each individual. And then in the generalized case, we train on 9 participants with 80% of their data. We reserve 20% of that data as validation. And then 2 participants out of the 11 are used only for testing. So that's our training approach there. And then our evaluation metric is accuracy. Can we actually predict with any kind of accuracy what tests this person is taking from their BVP signal? So, oh, I see a question coming in. What does 20% for generalized test data indicate? So that's the 20% of the train set. So let's pick 9 participants in the study. They each have a BVP window. We're going to take 80% of those snippets. I'm going to cut them up into, and we're going to train with those. And I'm going to take 20% of those and use them as the validation set. So this allows us to construct some graphs to see if we're overfitting. And so we actually want 3 curves that come out of this: our train, our validate, and our test accuracies as we train, especially for the deep neural network approach. So testing data has from same participants in the generalized condition too. No. So we reserve 2 participants that we've never trained on before. So like I said, so we have 9 to train, 2 to test. And then of our validation set is only the 20% of the data from the trained participants. Are these pilots because they fly aircraft? I don't know. It's all anonymized. I imagine them as pilots, but
actually how they name it,
right,
in the data set, they name as pilots. You can see it as participants. So if we roll back a few slides, it's actually some guys like wearing devices like this and doing this troop test, and they record by these consumer level devices with different type of signals. And to be specific, we only choose one of the signal for our this 3 pipelines to get some preliminary results, right?
Thank you.
Okay, so let's move on to feature engineering.
Yes.
Cool.
So let's take a look at one of these BVP signals. Our goal is to chop a 3-minute signal into a number of samples. So we have a window. We're going to take a window size of a few seconds, and this can vary, and this is a choice that we had, of how long that subsample is of our signal. And we're going to move that along and take snippets out of the person's signal and stack them all as rows in our data frame for building our test, train, and validate sets. So the time for each participant varies, of course, because these are individual testing conditions, but about 3 minutes for the baseline condition. And so we have, and if you multiply through by the sampling rate, 64 Hertz, we have about cognitive load condition. Like I said, each participant does vary because their individual test varies with the long they took on their so our job is extracting subsets of these data points, and one of those data points becomes potentially its own feature. And after we slice and dice the signal, we to shuffle the order of our data frame so that we don't feed in all of our cognitive load first and then all of our baseline second. So that's kind of the methodology of the data handling here. Hang on, we got a question. To overcome the limited data for the individual, have you considered training generalized plus individual models to improve models' performance on the individual?
So I think, with the presentation, I'll answer that. Yeah,
okay.
And just later.
Okay, perfect. And kind of just like on the data side, this process we just went through, we have our, we're pulling out, let's say our size is 1 second. We pull out 64 data points. And for purposes of our logistic regression, the only 2 features we actually want to look at or the ones that we found most useful after some testing, are the standard deviation and the mean of that 64 data point window. And going through normalization. Now, this is a kind of an idea. Is each participant should only be normalized with their own data. So, for example, if I have participant 2 and I'm making my generalized model, if I normalize all of my trained participants as a part of the same process, maybe participant 2 is really extreme. He's got really extreme standard deviation in values for his BVP, and he zeroes everybody else out. So it's important that normalization is conducted per person. And that's one of the we had. And so what we end up with, we have our final conditions for this logistic regression model. We have a standard deviation, a mean, label of what data set, either the baseline or the cognitive load, this is coming from. All right, so off to our pipeline 1. As I said before, for our logistic regression, we chose standard deviation and mean for each window as our features. We did try some other features from processing and Pearson correlation for different window sizes and such, but we find that those actually helped all much. So we those here. And feel that logistic regression is a great baseline approach. It's simple, less complicated, it's data to fit, and it could be uniquely suited for this small data regime that we are in. So let's look at our individual results we get. So this is, like I said, we each separately. So for pilot 0, their accuracy, not that great. Pilot 1, wow, 97% accuracy for a logistic regression on the standard deviation mean. Just, but notice this is not that stable a result. This very well for certain participants and others. And so we think that a sophisticated model might be able to help us decrease the spread and make this a more stable solution for testing. Also look at precision, recall, F-score. Absolutely. Future, we would love to compare these. We're being triangulated on what are the good features, what are the good models, and once we have a idea of where good accuracy is, want to add these. Let's see. So for the generalized models, so we're choosing 9 pilots to train. So we put them all together into our training set. We separate out 80% of their samples, and then with 20% of the remainder is our validation set. And the 2 pilots we've reserved aside, that's our test set. And we can see that our does drop from 79% or 79.6% 68%. So we do have a pretty significant drop in accuracy, and we maintain this very high spread. Again, it's not a stable solution. We have a small data set, and we're looking for something more significant. So that is to trying a deep learning approach. So we're going to take our standard deviation and mean. We found that was helpful. We're also going to feed the BVP in a feature. So we end up having, let's say for a 1-second window, 64 data points plus standard deviation mean, so 66 features would be the input here to the model. And hoping that a more complex model might be able to capture some of the features from the signal itself, and high accuracy. What we actually found was accuracy is lower, but the deviation of the test accuracies is actually much smaller, which is a much more stable result. It's again, it's difficult for deep learning in a very small data regime, and if we had all the data in the world, perhaps this would be a solution. So let's see, and then trying this on the generalized, again, train 9, test 2, 55 combinations, 64% accuracy. Again, we're 4% below just the logistic regression on standard deviation and mean. We also notice, though, that our drop is from 68% to 64%, going from individual to generalized. So we can see that there's less of a drop, there's less variability in the test accuracies. So the solution is more stable. It just doesn't have peak performance that we're...
Great. Thank you, Jacob. I will do the rest of the presentation on this Pipe 3 end-to-end deep learning. So our Pipe 3 is using this transfer learning approach, which is a two-step also. First, data preprocessing, make the bias and convert it to a spectrogram images. And then the second step is modeling. So we want to put our spectrogram images that contain time and frequency features of signals and send it to a deep CNN-based model, in this case, which ResNet 18 for this preliminary results. And in this pipeline, we believe using transfer learning approach or pipeline, it has some advantages. I will reveal it later. So in data preprocessing, we only use some basic signal processing, like doing some bandpass filtering. And of course, we need to normalize each pilot's data, just like previous two pipelines did, and also segment it within 1 second time window. And it's all for preparing for our machine learning model. And our signal to spectrogram with short time Fourier transform with Hamming window, and put scaling to emphasize the variations in the spectrogram. So within this, I would fairly basic signal processing, especially using spectrogram to capture time and frequency features. It will allow some more powerful model like ResNet 18. Of course, it's not like super, but it's much more powerful than logistic regression or DNN we just saw. And this transfer learning technique can. So in our modeling steps, because spectrograms dimension, it's not exactly as our pre-trained model, which means this ResNet 18 is pre-trained on a data set called ImageNet. And it like 1,000 in our case, which only has two classes. One is baseline, and the other another is this Stroop test or called it cognitive load. So in pre-trained model, it's on ImageNet, which has 1,000 classes, and it has over 1 million samples. So you can see the very different from what we have after we pad the spectrogram images, and we augment the data with time shifting and frequency shifting to make training more robust. But our trained sample and test sample, it's like 500, 600 in total for a test. So which is much lesser than the pre-training process. So it's where the transfer learning comes in. Tune all the layers of this ResNet 18 with only around like 500 or 600 samples of images, and trying to get some good results there. And yeah, ImageNet does not contain any kind of spectrogram images before, so which means our pre-trained model never seen any images that looks like spectrograms. So here we want to show transfer learning can actually, or this ResNet 18 can actually learn how to read from spectrogram images. Right, so jump into this individual test results. Our accuracy is around 60 to 97.8%. The average is 83.2. And if you look at the curve, it's barely overfitting, means our model, after fine-tuning, it learns well on spectrogram images and without overfitting. And yeah, we'll compare the results with other pipeline later, but you can see the soft accuracies or standard deviation of the accuracies are narrower. Then we move on to this generalized. We have this test accuracy range from 39 to 81. The average is 64. And if you look at this distribution plot here, actually our large proportion of 55 combinations that mentioned previously, which 9 to train, and the other 2 it's never seen in the training step. Actually, we have a large proportion of 55 combinations. It's over 60% accuracy. It's only a few combinations that's dropped below 50% accuracy. As I said, we didn't do much like fancy signal processing or optimization on 18. I would say it still yield pretty good results here. And at that, we compare these 3 different pipelines and get some from results. So you can see that our transfer learning model yields the highest accuracy compared to logistic regression and DNN. And also it's the learning pipeline is more stable, because if we look at the spread of accuracies or the standard deviation of accuracies, you can see though just logistic regression results, but the spread it's a spread than transfer learning. And of course, if you look at DNN model, it has narrows of test accuracies, but our transfer learning yield like almost higher than DNN model. So I would say in small data regime, we only got less than 1,000 samples to train in this individual test. I would say transfer learning pipeline we show here is have a good balance of accuracies and then we compare this generalized test. Logistic regression, it's accuracy average of 55 combinations, but transfer learning pipelines also yield some good results. Of course, as I said, no fancy signal processing or some into detailed optimization techniques are applied in our transfer learning pipeline, but still gets some pretty good generalized test results. So comparing generalized test and individual test, our finding is we recommend that training our machine learning model on individuals can yield better balance of accuracy and as we've seen from the results of individual test and test. And also our transfer learning pipeline works pretty well, especially on individual test. So and this type of small data regime that pilots of each pilots are different, and also our data set it's super small. So I would say we recommend training on each pilots or each individual other than generalize in such a small data.
And Johnny, can you talk about the 55 combination? What do you mean by these combinations?
Yeah. So I guess maybe I can roll back a little bit to here. Okay, since we choose 9 out of 11 pilots, so our generalized test, we choose 9 pilots for training, and that 2 pilots data that's never been seen before. And within this 9 pilots, how we choose these 9 pilots, because the combination of these 9 pilots could our model performance. As we said, if we look at the signal here, it's so different from each others. Each pilots are so different. So to be fair enough, we choose 9 out of 11. So total is 55 combinations. And we actually, in our code, we list all the combinations. And for the slides purpose, we only giving the minimum test accuracy and the highest test accuracy, the lowest and the highest, and of course the average of those 55 combinations. Did I answer that question?
I think so. Yeah. So sort of kind of a cross-validation, but in a more sort of meticulous and more conservative here. We want it to be very conservative and find the,
Right. And the reason why we put the validation in plot is because we want that focus on, okay, it's of training, we can further separate to train and validation. But we want people to focus on what exactly is the train and the test. The test has never been seen before, right? So yeah, close to actually the end of the presentation. So that's all we want to share today. Back to, conclusion or recommendation is when we develop this transfer or machine learning model, we want to deploy on each individual, we can yield pretty good accuracy and stability instead of you combine all 11 pilots, 20. Of course, if data goes to like bigger, you got 1,000 or 10,000 pilots or participants, that's another case. But within this small data set, in our results, so we recommend to have each person have their own model, especially using transfer learning pipeline yields pretty good results. Yeah, and all we want to share today. Thanks for your attention.